Welcome to Breadboarding. In the previous video, we were trying to get the ISA bus VGA card. So this is a Trident VGA ISA bus card working. And this is one of the tests we were doing, but every time we were scrolling text or the RAM in the video card was being accessed, we were getting problems. In particular, it was having problems particularly scrolling text. So what I decided to do in this video is I'm going to go back to the CGA card that I worked on a number of videos ago. And we're going to look at seeing if we can get that working a lot better. This is video 26 in the Breadboard PC 8088 version 2 series, and in this one we're going to be tidying up the CGA video controller. So this is the Trident VGA card, so this is an ISA bus card. We're only using the 8-bit part of the ISA bus, and it had a standard VGA connector on there. Now, originally when I wired this up, it's just wired directly into the bus rails here. But as I was trying to sort out some of the problems with it, I put in some extra buffers here just to see if that would make anything any better. It did improve a little, but it didn't actually fix it. So what I've done is I'm going to put this to the side for the moment, just so we can finish off the series. And when I look at the next project, then I'll look at perhaps trying to get this working better then. So what I've got here is the original CGA card. There's an awful lot of debugging cables. So this is the logic analyzer. A lot of these cables are all the logic analyzers here. I don't want to disconnect any of these things because invariably when I disconnect stuff, then I dislodge something and it actually then takes a while to get it all working. So that looks a bit of a mess. Underneath that, then the wiring, in fact, isn't actually too bad. It's primarily the logic analyzers there. So what we're going to be doing is looking at how we can actually improve on this. So in our high-level plan, we're almost at the end here of trying to get the disk, mouse and Windows working, and we've kind of given up for the moment on trying to get the VGA video card working reliably, and we're going back to the CGA video controller and also going to try and run Windows 3.0. So to start with, where we left the CGA card previously, there were a few problems with it. So this is a BIOS screen. You can see that on the right hand side and the left hand side here that the text was kind of being cut off, and that really the pixel data needed to be a delay of about one dot clock cycle. So some of those changes have been done, and then some further changes, so that's actually tidied things up a bit. You'll also notice that some of the test patterns I was using, that in fact on the attributes here you can see there's a white line. You can see that the attribute kind of is not actually covering the whole cell. So again, there were some timing issues there. And you can also see at the top here that some of these had the attribute sort of leaking over between cells. So that had been fixed. And also in the 40-column mode, you can see here that we've also got the attributes aren't quite lining up properly. And you can see up here as well that they bleed from one cell to the next. Those have now been fixed. This is one of the block diagrams I've used in the past to explain about how the video controller works. We have the Motorola 6845 compatible cathode ray tube controller chip. We have some quite fast static RAM. This is 15 nanoseconds static RAM, which is much faster than the dynamic memory that was used in the original VGA cards. We have a character generator EPROM that has the character bitmaps in it. And you'll see over here that we used a complex programmer logic device, the ATF1508. So this is a 100-pin chip, and we're able to actually take a lot of the chips in purple here from the original design that I used in the Breadboard PC version 1, and all the things which are in purple are now actually included in this complex PLD. We still have the video digital analog converter. There's a couple of latches we're still using and the shift register, and we're using the 25 megahertz dot clock, which controls the individual pixels. Now in the original Nanocomp series, the 6809 series, I had a couple of videos here on fixing the video snow. So this is what happens to the video display when the CPU is accessing the memory at the same time that the cathode ray tube controller is using the same RAM to display things to the screen, and you get sort of this sort of interference, otherwise known as video snow. Now, in the original Nanocomp 6809, I used this in the Breadboard PC Series 1, and we ended up actually adding a couple of extra PLD chips here. So we have this sort of latch here that connects to the main CPU data bus, and then we've got a PLD here, and then also a flip-flop here as well, because of some of the limitations of these older PLDs, couldn't do certain things. And with all this stuff, we managed to get the timing such that we're able to interlace the CPU access to the video RAM with that of the CRTC. And this was actually what came out of it. So out of all of the original 6809 version of these are all the changes and things I actually needed to do in order to get it all work. And so what I'm doing now is really applying a lot of these changes to the configuration that we have at the moment. And the key thing that we do here, and shown in this diagram, so again, the purple is the stuff which is actually in our complex PLD. So when we're actually writing data to the video RAM here from the CPU data bus, what we're actually doing is we are latching the addresses that we actually want to access on the video RAM in these latches. So we don't immediately pass through the address to the video RAM. We wait until an appropriate time when the CRTC is actually not using the video RAM here. And what we also do then is latch the data from the CPU into this bidirectional buffer latch here. And then when it's the appropriate time, then the logic here will enable the various signals here such that it will output the CPU address, it will output the CPU data, and will actually write the data into the video RAM. It will try and squeeze that in between the cycles where the CRTC is actually accessing the RAM. Now that's easier said than done, but in the previous series I managed to get this done, but it does take a lot of messing around to get this done. And what this results in is, because the video RAM there being accessed by the various latches that drive the video output, that because we managed to synchronize that, we don't get any snow. And then on the reading, then in a similar way, when the CPU says, can I read the video RAM, what we do is we latch the addresses here. We don't pass the addresses through straight away. And what we then do is, an appropriate point in time, the logic here will say, output the video address here, take the data here and stick it in this buffer here. And then at a later point in time, we'll then actually put that on the data bus so that the CPU can actually read the data. And again, that's done such that when we read the video RAM here, it is done during a quiet period when we don't need it for outputting here. So again, that should eliminate the video snow. So this activity has gone on over probably about 6 weeks. So where we left the CGA card previously was version 7 of the CGA video PLD, and this was in videos 16 and 17. I'll include links for some of these videos in the top right hand corner of the screen, and there'll also be links in the description below if you want to go and have a look at those. And basically, I'm not going to go through all of these, but between version 7 and the current version 13, it's gone through a lot of iterations of fixing all sorts of issues and enhancing it. And all I'm going to be doing really is just showing you a comparison of all the changes and what the finished state is. As we were going through a number of these bits here, then there were quite a lot of interference issues and things I had to deal with. So if a quick look at the comparison of the two versions of these PLDs, and you'll begin to see, if we were to go through this in any great detail, it would take a very long time. So this is comparing version 7 with version 13, and you'll see here that version 7 was back in July 2025, and this is just a day or so ago, so the 11th of December, and I've been working on this, and we've gone through a lot of versions here. So this is the CUPL definition, and you can see here this is just our layout, and you'll see a lot of where we had blank cells which weren't in use have now been used, and these various additional functions and latches and things have all actually been put on here. There was one strange problem that I did run into, in that the CGA RAM input into here, under some circumstances when I updated the PLD configuration, there was actually signals being output on this, and it was causing all sorts of trouble. So in the end, what I did is I moved the CGA RAM from this pin here down to pin 53, and the problem went away. So whether it's to do with a problem with my particular chip on that pin, whether it's to do with a software bug somewhere in the WinCUPL, I don't know. But by moving it from there to there, I managed to solve that problem. And that probably caused at least a couple of weeks worth of delay. So a lot of the additional functions that we needed from that anti-snow stuff have actually put into the chip here. There's a lot of comments being added here as well, so I will upload all of these files into GitHub for anyone who wants to have a look at them. And the version 13 one is the one I would look at. The earlier versions, there's all sorts of strange things going on in there. But this one has been quite heavily commented, and there are a couple of things I had to introduce. So the clock here, CAB, CBA clock, this is actually a combined clock signal that we used to have for the 646 latch in some of the diagrams I was showing you previously. We've ended up using the data terminal ready signal to control the direction of the data bus buffers. The advantage of DTR over the memory read, memory write is the DTR signal is a little bit wider and it gives us a little bit more time for signals and things to stabilize. We've also got the bus ready signal coming out here, so this allows us to introduce wait states into the CPU. So if we need to slow the CPU down to allow ourselves to read and write the data, then that allows us to do so, and that's what we covered with the VGA card as well. This is where some of the more major changes are. Some of these nodes here are actually where I've had to create intermediate results, where some of the rules were getting too complex. What I've ended up having to do is to assign some of the rules to these values here, and then these values can then be included further on down the line. We'll introduce slight delays, but this was necessary where I was running into things where the PLD design was getting too complex for it to fit in the 100-pin version of the chip. Now, a lot of the rules here use the dot clock cycle. So the dot clock cycle we define as the number of dot clock cycles from the start of the CPU access, so whether we're reading or writing. And then the CQ cycle is where we start the access within the overall dot clock cycle. What this basically allows us to do is to determine what the timing should be depending on when the CPU starts accessing the video memory in the actual CRTC cycle. You'll see there's lots of different versions of things where I've been trying various things. There was a strange problem I ran into in that the clocks that we have here, so the QA, QB, QC, QD, basically count from 0 to 15 to establish what the different timing signals are for the CRTC. And what I was finding is when I was changing from the low res 40 column mode to the high res, then the clocks were getting out of sync. The Q reset will make sure that all of these flip-flops are actually coordinated and zeroed when the clock speed changes. I've had to tweak a number of the character clocks and the attribute latch and shift register latches. I've disabled some of the black and white mode, so this disables the color signal when working with, say, an RF modulator for a legacy CGA TV output. It's not really necessary for what we're using, so that's simplified some of the rules slightly. This is part of the logic that actually produces the reset for when the resolution changes. So this just means that when we switch from the 25 megahertz clock down to the 12.5 megahertz clock, it will make sure that the various flip-flops are actually reset so they all start at 0. I was getting strange problems where they would be indeterminate states during the cycles and we're not counting in the correct sequence. You can see that's where we disabled the black and white mode. Now down here, this is basically where we're making use of all the latch information. So these are the latches that replace the 74LS646 bidirectional buffer stroke latch. So this is where quite a bit of the complexity in all of the configuration comes from. And this is where we changed from using the memory read to the DTR. And the reason for that is that this signal here is slightly longer than this one here and gives us a bit more time for all the signals to stabilize. We've had to change some of the rules to do with the output enable for the video RAM as well to increase the amount of time that we've got available for that. And this is where these intermediate terms, so this is where we're defining specific nodes here which have actually got the rules for each of these various cycles here. Each of these cycles here could have 3 or 4 terms associated with it, and when we're combining all of these various things a little bit further on down, it was getting a bit too complicated for it to work out. Then the address output enable this is where one of the first areas where we have for the different CPU cycles and the various modes, then which dot clock cycle should we have certain signals. starting from. And what we'll be looking at is the address output enable. This is where we're taking the CPU address and we're feeding it into the video RAM. And so we need to time this quite carefully to fit in the slots where the CRTC is not needing to access the RAM. The address clock basically clocks the CPU address into the latches at an early part in the cycle. The dot clock Q0 to Q3 is the underlying flip-flops that generate the dot clock cycle. There was an additional bit here where I needed to prevent where the memory access cycles were extending beyond dot clock 0 to 15. I needed to implement a bit of logic here to stop the various clock and latch signals appearing multiple times within a CPU access. And then we can see here the clock BA is basically the timing signal for reading the data out of the video RAM and putting it into the latch. And you can see here that we're making use of the various CPU clock cycle and the dot clock cycle in order to work all that out. And this is where some of these had too many conditions when they're all being combined together, and so that has simplified that. And so what I'm going to be showing you now, I'm just going to go through some of the tests and show you the test program I've been using for this. So this will be similar to the test program that I used in the earlier videos. So CGA Test 11 has basically taken some of the earlier ones that I've gone through in some detail, and we're now actually added a few things in here where I was deliberately overwriting the same area of the screen in a very tight loop to generate video snow. And what you'll see is when we run this now, we won't actually see any video snow. And I'll show you through screenshots where we've taken this from earlier on in the development to actually show where the snow was occurring. This is a screen from the medium resolution graphics mode for 320 by 204 color. And what this basically indicates is the test. What it basically does is write to sending values to every single byte in the video memory. It then reads the value back, and if the read value doesn't match the written value, then it'll actually write out a solid bar here. So what this indicates here is out of all 16K of the video memory here, there's probably just been a handful of situations where it hasn't been able to read back the same value that it's written. So this is actually, when it started, then there was a lot more of these bars on here. But as you get to the end of the cycle of tuning this, then you get a smaller number of things here. And this is similarly in the mode 6, which is the high resolution 640 by 200 two-color graphics. And you can see here that where we're doing a test write, then a read, then we zero the value, and then if the written and read value were not the same, we write F here, which gives us a bar. So you can see in this particular mode at this point in time, there were a lot more issues with that. And then the test program was further enhanced, and basically what I did is where I was doing the test and we found the situation where we were outputting a bar, what I did is I outputted to the power on self-test register the address that we expected, which also matched the value that we were expecting as well, and then output what the read value was. And so you can see down here we've got various values and things of, so we could help to diagnose this. So you'll see here that the D7 there, F7 there, and when we look at here, what we're doing here, we are writing to the address D7, the value of D7, but when we read it back, what in fact we find is we've got F7, and so what we end up doing is writing out to the log. We'll have D7 is the value we're expecting, but what we actually found is F7. So we're writing our D7, the address D7, we're reading F7, and then we're writing the FF out to D7, which gives us our bar. Then here is just drill down a little bit more detail, and what we can see here, the write of D7 value to D7 was off to the left here over here, and then what we've actually got here is we're now actually trying to read the value, and you'll see here that the memory read cycle ends over here. So this A1 is where the CPU will actually read whatever value is on the data bus at that point in time. And in fact, the problem here is that we're expecting D7, but in fact what we do is we read F7. And why is that, of course? So the value in the address is D7, So this clock here is where we take the video RAM data and we put it into the latch where we can then use it for the CPU to access. But the problem is, from when the address changes here to when we're latching this, there's only about 14 nanoseconds from the address to this clock, and the RAM is really 15 nanoseconds or higher. So we're dealing with sort of probably about a 20 nanosecond period here that we need as a minimum for the video RAM to be read properly. And so what actually happens, I suspect, is that the data's in the process of changing when it gets latched. And so rather than coming out as D7, it comes out as F7. And so what we have to do is we need to delay this signal here, probably about half of a pixel, which is about 20 nanoseconds. So we're dealing here with timings down to 10 or 20 nanoseconds, and when things get out of step, then that's when problems occur. And then this is sort of just showing the screen here with these are the byte values, so the address and what the expected value be, and then what the read value would be. You can see we would be writing 1.5 at 1.5 address, and then we're getting back 9.5. So it probably indicates that the data lines are in the process of changing, but we're just latching things a little bit too early before they've all fully stabilized. So let's take a look at some of the tests first of all. So I've actually got the Breadboard PC running, and we'll just have a look at the video capture. I'm just going to run the test program. There's not a huge amount to look at on the display here. You should just see the flashing cursor here. Now this is the first test that I was doing, where I output a single block, and then what I do is, in a loop, very tight loop, I update the screen and actually overwrite the block again and again. Now when I was first doing this, I'm just doing it at the moment, the whole screen would be filled with random data as it was accessing it. But in fact now you can see there's no interference whatsoever. So what we're able to do is to read the data and write the data to the video RAM when we're not using it for the CRTC. Then we've got some of the standard test patterns I've used in previous videos, but you'll notice now that generally everything seems to fit okay, and all of the attribute data should be sort of properly contained within the characters. Then the blinking. Then this is the scrolling. So this is an example of the scrolling data that we covered in the previous video. So if I scroll this, you'll see that in general we get the scrolling occurring without any loss of data. Occasionally get the odd attribute that doesn't quite get handled properly, but it generally works pretty well. Then we've got our 40 column mode. That's all working. Now this one here is now actually in the medium res graphic, and if I press that button there, what that is actually doing is a very tight loop updating the screen. And as I was doing this, you would have seen that this screen would have been filled with a little orange minus signs, but that's working nice and cleanly now. And then we're actually updating the whole screen and writing orange bars where the data that we read is not the same as what we write. So that's all clean. And now we're going into the high res mode. And you'll see here, this is the high res mode. And again, now if I press this, this previously would have been filling the screen with lots of random snow, and it's now clean. And now if it does the refresh the whole screen, you'll see a slight flicker there as it does it. But basically there are no problems with any of the data being written and then read. So that test seems to work quite nicely. So now just reboot this and we'll actually run up some of the other test programs. I'll speed this up whilst we do that. Here are the tools I've been using. So you'll see the disk test here that will run a little bit later just to check that the disk is working properly before we run Windows 3.0. We've also got a little simple one. So CT4 is the first test that we did. And you can see here that generally it's coming out quite okay. There's the odd little time when we get a little bit of interference. And this is when it's using the BIOS video access routines. But when it uses direct write to the video memory, then generally it's much cleaner. And that previously was coming out quite messy. Now the only interesting thing I found about this test is that the first page of the test is actually running the graphics card actually at the wrong frequency. I'll show you this in a minute. The reason why we're actually getting a bit of interference as this screen has been updated is that what I discovered is it in fact This is actually running this at the lower resolution at the 12.5 megahertz frequency, not 25 megahertz, which is why this is actually not working quite right. But the later modes that are actually working correctly, however, the video data has already been written. And if we run the CGA comp program, this is the one that's the CGA compatibility program. This is the one that we have the most tests. And probably the most significant one here was that originally the CGA Snow, when we ran this, you would end up with sort of a green snow occurring all the way down the screen quite a lot. And in fact, when we run this now, there's no snow interference. Very occasionally you might get the odd attribute would change, but this is basically updating the screen in a very tight loop. And you can see that there's no snow there at all, which is great. Then these are some of the other tests we'll just run through. I'll speed some of these up as we go through them. I won't talk over all of them. This high-res one goes through all the various colors. When you run this, the synchronization of the monitor slightly misses out the right-hand line there, but you can see it did appear when it first came up. Sync on the video capture card sometimes can't quite cope with this one. A lot of these tests, when I was doing these previously, were coming up with lots and lots of problems with them. And probably the more interesting ones are the various compatibility ones here. So we can see that we're not running at 60 hertz, we're at close to 70 hertz because this is producing VGA output. You can see because we have those bars appearing here, then it means that we are using a proper 6845 compatible cathode ray tube controller chip. You wouldn't get that on a lot of later video cards. This is changing it to the sort of high color block sort of combination of text and graphics mode. This is just changing the timing to move the display screen. And this shows how we can move the display just by changing the start address in the video controller. Move things around the screen in that way. And this is what some of the games would actually make use of this scrolling mechanism in some of the later games. Text colors. There's generally a few pixels on this multi-burst pattern that don't come out quite correctly, but the vast majority do. And this is one of the standard test patterns. Again, there are a few minor pixels here that don't come out quite properly, but it's generally a lot better than it was previously. This motion test plate, when I was developing this, then this was coming up with all sorts of problems, pixels left behind, whereas now this runs completely cleanly. So whether it's going horizontally or vertically, previously there would be pixels left behind from time to time when the timing wasn't quite right. This is a good test of the timing in the 4-color medium res graphics mode. And then it's just interesting for some of the video RAM benchmarks. So because we're using quite fast RAM and we're also using a 8 megahertz CPU, then in fact you can see here that our video RAM is read at a speed more than twice the original PC speed. We can write almost 3 times faster than the original PC. And the interleave mode's about twice as fast. Okay, so we can see that those tests are coming out quite well. There's one other set of tests that I did run as well. So these are similar to the VGA ones. The menu is not terribly easy to see, but I'll just go through these tests. And a few pixels on that multi-burst test. and then it just cycles through the test. So that all seems to be working a lot better than it was. There's the odd occasional pixel I get which isn't quite right, and I'll come on to that in a few minutes. So basically these things seem to be working a lot better. So what I will do now is I'll run a disk media test. So we'll do that, and then we'll try and run Windows 3.0. I did install this earlier, so I'll show the setup screen, but I have already installed this a little bit earlier, and we'll show that actually starting up and running. So I've run the disk media test, so that all seems to be coming up okay. So I've already installed Windows 3. The setup program is much more familiar for Windows 3 than the previous versions that we looked at in the previous video. So this is the configuration we've got: MS-DOS, CGA, PS2 mouse, and the UK keyboard. Now we're just going to run Windows. Might need to do this a couple of times because it is a little bit unstable. There we have Windows 3.0. Now, unfortunately, the mouse isn't working at the moment, but it was working a little earlier. And there is a little bit of interference on the rest of the display there. You can see there's the odd pixels which are not coming out quite right. You can see here we've got Program Manager, Real Mode, 383K or free memory. We'll just finish that. So I'll try and get the mouse working, but the main thing is here that with all those changes, I've managed to get the CGA video working a lot cleaner than it was previously, and we've also now got the Windows 3 working. I just need to work out why the mouse wasn't working in that situation. So this is the test mode, which is testing mode 6. So this is the high resolution 640 by 200 video mode. And you can see here that with CT6, it should be having the high res flag set to 1 and the BW640 set to 1 with a 25 MHz dot clock. However, when I had a look at the logic analyzer for this, you can see here that down the bottom right hand side here, this is where the high res signal is, and we can also see the dot clock signal there. And what you can see here, that the high res signal is actually low, which is what it is also when we're using the lower resolution modes, such as the 320 by 200 graphics and the 40 column mode. You can see here that the dot clock here, and we've highlighted up here that in fact the frequency here is only 12.5 megahertz. There should be 25 megahertz. So that would explain why sometimes using the CT6 test, then it was actually causing some confusion because the test itself is not setting the control register to the correct value. I also had during the project here, the IDE Disk controller was showing a bit of instability. It still occasionally is a bit unstable, but what I found in that the original Compact Desk Pro actually had these 1K pull-down resistors on some of the data bus lines coming from the IDE drive. So I ended up putting the pull-down resistors on the top D8 to D15 lines, and that was partly because they were connected to the 646 latch, and apparently the 646 latch has a lowered voltage, the low value of 0.6 volts versus 0.8, and because some of these values were floating a bit high, higher than 0.6 volts, then it needed that pull down for it to work properly. So that has stabilized the disk accesses, as you can see from the media test that previously completed. So I'm just going to review the final state of CGA board. So this is the CGA card in its entirety. So over here we have our VGA connector going off to the VGA to HDMI converter, and then there's a video capture card plugged into the laptop I use. This is the main complex programmable logic device here that I've used. So this is the 100-pin ATF1508. Now the only issue with this really is that I had to mount it on one of these breadboard adapters, and really trying to get 100 pins connected some of the pins were plugged into the breadboard, but the majority of them were having to use all these cables. So it is a bit messy. I'm not sure if I'd necessarily use one of these again, but it certainly is quite powerful and flexible. I did have quite a few strange things going on with it in the later stages, so again, I may avoid these particular ones in the future. If we just take a look at what the card is, I did actually add a little bit in here. Down the corner here is another decoder here. I wanted to make sure this card could actually work standalone, because in the next project I'm thinking of doing an Intel 386 based breadboard PC, I wanted to have a standalone CGA card, and because there were one or two control signals that I needed to get all the way over from the other side of the board, I decided to make this sort of standalone. So this whole card is just a standalone CGA card, can plug into an ISA bus connections, and hopefully will work. I was just going to have a look at how I could have improved the anti-snow changes. Now, when I did the original monochrome display adapter card, I actually used a 4K static RAM, which was dual port. And what dual port means is it's got two lots of data lines and two lots of address lines. So it means that basically the cathode ray tube controller can access the RAM, and also the CPU can access the RAM without actually interfering with each other. For this monochrome display adapter, I only needed 4K of RAM, so it wasn't really an issue. Now, the only issue with this particular chip is that it was a 48-pin chip, and unfortunately they're no longer made anymore, and the price went from about £10 or £12, $15 or so, up to over 20, 22. I haven't checked recently, but they almost doubled in price, so they were no longer being made. And to fit 4 of these chips on the breadboard for 16K of RAM would have been quite difficult. As I've been using some of the flat pack chips, and in particular the 100-pin chip, I thought, well, perhaps I'll have a look at what chips are available in larger RAM sizes. And in fact, there's this particular one, which is a 16K by 8-bit dual-port static RAM. So this is very similar to the one I just shown you, apart from it's got 4 times the amount of memory, but it still has all the duplicated data and address lines. So basically, if I was able to use this, then I could actually swap out quite a few of the buffers and things that I've currently needed to use, and all of the latches, and an awful lot of the anti-snow logic becomes irrelevant. So I've actually ordered some of these, and if we have a look at the pinout here, you can see that there's the TQFP 64-pin pinout, and if you just have a look down here, we can see this is a 14mm by 14mm, and this means the pins, I think, are the 0.8 inch pitch. And it just so happens that Proto Advantage do a appropriate adapter. So this is the PQFP64, the DIP64 adapter. So I'll be able to solder the chip onto the top here, and then we can access it through the 64-pin DIP adapter. So I think that's going to be a lot easier to actually use on the board. And what I'm going to do is to have a look at reworking this at some stage. I'm going to finish this project now, but I'll have a look at reworking the CGA card to use this dual port static RAM, and to probably be able to pull out some of the buffering and things that I've got in there already. So that's on order. I'm really looking to do that sometime in the new year. So if you look at the board here, this is where the current 32K static RAM chip is. So this is a 15 nanosecond access time. So we have a lot of address buffers. So the buffers here are between the cathode ray tube controller chip here and the RAM. And then there's a couple of buffers here, which are between the CPU address bus and there. And then we've also got assorted decoders and some more buffers and things. So I think probably by using this 64-pin chip, we can probably get rid of certainly these two up here. And so I think I'll be able to rework the board without actually having to do too many changes. And that should hopefully make it much more reliable, and it shouldn't have any of this sort of interference that we've been seeing. And this is showing one of the test patterns that I showed you early on in the video. So I've pretty much come to the end of what I wanted to do with this project. So the version 2 of the Breadboard PC, I'll actually go through a summary of it probably in a week or so's time. I'll do a follow-up video where I'll review the things I set out to do at the beginning and look at what worked well and what didn't, and what I'm going to be looking at in the future. I'm certainly hoping to be able to try and do an Intel 386 breadboard PC starting sometime in the new year. So thanks for watching. If you don't want to miss out on future videos and future series, then please hit subscribe. And if you could just hit like as well, it just helps to make the videos available to more people. Thanks for watching.